Thank you. Well, first of all, I'd like to thank the organizers for inviting me to give a talk here. And also, I'd like to apologize that there will be no relativity, general or special for that matter, in the talk. There will be, however, propagation estimates, microlocal analysis, limiting absorption principle, spectral and scattering theory, and the Feynman propagator will also show up. All right, so the majority of the work that I'll talk about is joint with Jian Wang at UNC and Maciej Zworski in UC Berkeley. And without further ado, let me just jump straight into PD. So the motivation comes from fluids. I'll talk about it a little bit, but we don't necessarily care about non-relativistic fluids today, so I'm not going to dwell on this too much. So I'll just look at it as from a PD point of view. Here's an initial boundary value problem for a fourth order differential equation. My Laplacian is the partial x1 squared plus partial x2 squared. So you have a domain in R2, smooth, connected, simply connected, bounded. I'll make some assumptions on it later. And we're solving this differential equation where the weird part is that you have a fourth order term appearing here. So it's dt squared times the Laplacian. Nevertheless, you can solve it locally. It's a linear PD and it's solvable. You have a Dirichlet boundary conditions, and you have the and then you have the initial data equals to 0. Place it in. So where's the data for the solution? Well, the data is in this forcing term. So this is subject to internal forcing with frequency lambda 0, which I will take strictly between 0 and 1. It turns out to be the right choice. And with some profile, which is just a nice test function inside it. Right? Now, this equation has local, global well-posedness. The question is, what happens to the solution as t goes to infinity? Right? But perhaps it's a weird-looking equation. And of course, many people can write many weird-looking equations, and it's not really a good reason to study them all. There is, however, a motivation. So this is not the first time this equation was written. And maybe I'll just say the words because it'll take a while to write. But one of the motivations comes from oceanography, actually, and the attempt to understand internal waves in the ocean. Now, I should say that the kind of phenomena I'll explain has never been observed in the real ocean. It has, however, been observed in a lab, which is, there's many reasons why it's not the same as the real ocean, but enough people from the oceanography community thought that it's interesting enough to bother actually setting up an experiment. And so I'll draw an experimental setup here. So that's what they did, up to maybe flipping something upside down. So they took a tank of water, shaped like a trapezoid. Turns out if you make it straight, it's not what we want to happen doesn't happen. Okay, but you can think of the ocean bottom as being like this, and if you start asking questions like, well, the ocean is more wide than it is deep and stuff like that, then, then we'll be here forever. But in any case, that's what they did. So they did this, and so that's our omega. And I know it has corners, but yeah, and in our case, it won't. And then they filled it up with water, and then they stratified it. They made it a salt solution so that it's heavier at the bottom, okay? That's, again, something that supposedly happens in the ocean. It's more dense at the bottom. And then what they did is actually the side of the aquarium is movable, and so they shake it like that. Okay? So when I give a slide talk, then there is a movie of what happens. Here I'll just have to describe in words. So you have water here, water, well, really brine solution. That's how they did it. And then you start shaking it. Okay? And then what you see that they have some kind of coloring so to see what's happening. If you shake it at the right frequency, so they shake it at frequency lambda 0, and if you choose it right, depending on, well, various physical parameters and also on the shape of this trapezoid, then a pattern emerges after a while, which is, it's a nice video to watch. I'm sorry I can't show it today. But what you see is that somehow most of the shaking localizes on what they call an attractor. It's not that water stops shaking here, but it's somehow most of the shaking, if you want the singularities as time goes to infinity, seem to localize on this attractor or after a long time. And so that's the kind of phenomena that we'd like to explain. And I forgot to say, so their aquarium was relatively thin, so it's a 2D problem for them. I know the ocean is three-dimensional, but many things happen in the ocean that don't happen here. All right, so I should say who these people were. So it was first predicted that such attractors would appear by Mas and Lem in 95. And then the first experiment was by Mas, Danieli, Someria, and Lem in 97. And there's also works by the Dossois lab at ENS Lyon, and in particular the thesis of Brouzet is very nice to read about various, there's a multitude of questions asked about it. All right. Now this is as much as I'll talk about the physics of it all, but at least it's something experimentally observable, and it's interesting to see why does this attractor appear, how does it depend on lambda 0, and so on. Now there's a list of previous work here. I'm not going to list those names. I'm not going to pronounce all those names. But basically, there were people who were interested in these problems for various reasons and related problems. Some of them connected to fluids. There is actually another model of a rotating 3D fluid, which leads to a similar equation. And of course, there is a lot of simplifications you have to do to get to this linear equation, which there is a whole list of words written, and I can pronounce them if somebody asks me. But I have to admit, I don't know how the derivation works, but I know that the physicists cared enough to use this linear model in their approximations. And it does, the results we get are compatible with what they see in the tank. So there's this batch, and then Colin, Dirichlet, and Saint-Amand renewed interest in that problem. And they wrote a paper that did it, that explained this phenomena microlocally without, but they didn't have a boundary. They didn't have boundary effects. Instead, they had some general zero-Thorer pseudo-differential operator on a torus. And then Zworski and I revisited that from a different point of view. You know, the French used Moore theory, very periodical, and we periodically used radial estimates, which originate in the work of Maciej's advisor and my grand advisor, Richard Melrose. Yeah. And then there were later works on various related aspects to this problem. Okay. Okay, so now let me get into the math. So how do we study this problem? Well, we can try to use spectral theory, right? At least we can write a solution using spectral theory. That nobody can stop us from doing that, since this problem is stationary. So what you can do is you can rewrite it as the following equation. So maybe I'll do 2 here. So this is going to be spectral theory. So what you can do is, you want to think of it as a kind of a wave equation, but the wave equation doesn't have the Laplacian, it has just dt squared. So you factor out the Laplacian. You look at the Dirichlet Laplacian, the usual one. And then you write it in this form, and you get this problem where you just have dt squared, and then you have this operator p. But of course, there's a price to pay, because you also have to factor it out on the other side. And so the operator p that you get is this, is partial x2 squared, and then the inverse of the Dirichlet Laplacian. Now, if you look at the mapping properties, the natural thing is to think of it as an operator from h minus 1 omega into itself, right? This is so far nothing but really elliptic, usual kind of elliptic boundary value problems for the Laplacian, right? Now, if you look at this operator, so it was known, I think the work of Rolston is the one that showed this, is that this operator on the space h minus 1 is self-adjoint. It's bounded. Well, it's easy to see it's bounded, right? Because you anti-differentiate 2 times and then you differentiate 2 times. It's easy to see it's a bounded operator. You can show it's a self-adjoint operator. That's also easy to do. And with a little bit more work, you can see that the spectrum of this operator, so the spectrum in terms of spectral theory, just as a set, is always equal to the interval 0, 1 for regular enough omegas. Okay? And so you see that you got yourself a nice PDE with, or you can use spectral theory now to write down the solution of this equation. It's just the operator is a bit weird, right? If you didn't have a boundary, then it would be zeroth order pseudo-differential operator, right? This would be order -2, this would be order 2, and then you would get zeroth order. But here you have a boundary, and boundaries are notoriously annoying to handle. So I'm not going to try to embed it into any big algebra of pseudo-differential operators. We use somewhat ad hoc methods with reduction to boundary ultimately. So, well, how can we write the solution then? So this is if you taught a general, ODE course or any course on Fourier method, you know that you should just diagonalize this operator, right? And then you just get an ODE. And this is one of those things that, at least when I learned physics in school, it was taught under the name of resonance. When you have a harmonic oscillator and then you try to perturb it at a fixed frequency, then if the forcing frequency is close to the proper frequency, then the solution grows, right? And if it's far, then the solution stays bounded. And that's the kind of thing that we'll see here, except of course here it's a PDE. So the proper frequency is really a range of frequencies in the spectrum. But in any case, what you can do is you can write this very simple formula in terms of the calculus of the, usual calculus of the operator, like that. Hopefully I write this one right. There you go. Here's our solution. And you understand this as a function of the operator, right? It's a function applied to that. Okay, so for example, that gives you well-posedness, at least in some sense, immediately, because, well, here I just sort out the solution, right? What you can see is that the part of spectrum of P away from the square of the forcing frequency, well, what does it give you? So if lambda 0 square was not in the spectrum of P, or if we somehow excise that part of the spectrum, then you see, well, cosine is a bounded function, right? This is bounded by 2, and here the denominator will be bounded away from 0. And so you're going to get something that's bounded in the energy space. So if you didn't have the spectrum near lambda 0 squared, then you would get an H1 norm bounded by constant as time goes to infinity. Okay. Now in our work, we'll only study the spectrum near lambda 0 squared. So for the rest of the spectrum, we'll just have to settle with the remainder like that. That's somehow something that's bounded in the energy space. It's not small, but it doesn't create extra singularity. So somehow this attractor that you observe, it's less regular than H1. And that's why it can stand out with this kind of bounded remainder as a background as time goes to infinity. All right, so what we need is we need to understand the spectrum in some sense of P near lambda 0 square. Okay? So that reduces it to a spectral theory problem, a very familiar kind, but for a slightly unfamiliar operator, a zeroth order operator. Now, well, how do you study spectral theory? Well, it's a whole, there's whole books written on spectral theory of much simpler looking operators even. But one of the things that you can try to do is you can look at eigenfunctions, right? And this is not going to cut it for this work, but it's going to give us useful information about what to look for in general. So in the end, we'll discover there's absolutely continuous spectrum and there are no eigenfunctions. But let's look at eigenfunctions first, even though we'll show they don't exist in our regime. So eigenfunctions. It's the simplest thing to ask about the spectrum, right? So, so let's look at a very simple spectral problem, which is I take P minus lambda squared for some lambda, and then I want to apply it to something, and I want to make it 0. And this inverse of the Dirichlet Laplacian was useful here because you get a self-adjoint operator and you can use spectral theory, right? But for the actual PDE study, it's cumbersome. So it's good to factor it out again. So that's why I'll write my potential eigenfunction in this form, like that. Laplacian of something here. And then I should be looking for W, which is an H1, right? Well, since this will have to be revised anyway, let me make my life considerably easier. Just look for smooth eigenfunctions. Let's just get some intuition of what smooth eigenfunctions would look like, even though they don't exist. So, all right. So what happens here is that this operator, if you look at the equation you get, it's kind of a bit of back and forth factoring and then putting back this Laplacian. But you see that this operator, which I'll call P of lambda, this is just, I should be able to write this one down, right? It's just dx2 squared minus lambda squared Laplacian. There you go. Constant coefficient, second order differential operator, right? I mean, it makes sense. We just started with the evolution problem and replaced dt squared with lambda squared. Right? That's what we did. All right? So this is nice. We know how to handle second order differential operators. But one of the unusual things is that the spectral parameter is featured here, right? The usual thing you're looking for is minus Laplacian minus lambda squared, and this looks different. Now, if you look here, my lambda is going to be in the interval 0, 1. Very close. Well, I'll do the computation. Okay, it's minus lambda squared dx1 squared plus 1 minus lambda squared dx2 squared. What is this? It's a wave operator, right? It's a 1 plus 1 dimensional wave operator, except it's tilted. Not the constant is not. So this is wave operator. 1 plus 1 wave operator. Okay, there you go. Now, what's funny is that we're not trying to solve the causal problem for the wave operator. Of course, it was already explained in the first talk that it's, the problem is with Cauchy, not with the wave operator. And here, from a physical point of view, solving the initial value problem makes no sense because the vertical direction is not time, it's gravity, or the stratification of the fluid. Right, so this is not the problem we should be solving. Instead, what we have the boundary condition that I forgot to put in. So we have a 1 plus 1 dimensional wave operator. You see, if you're a PDE person, at this point you can forget about fluids. You have a 1 plus 1 dimensional wave operator on a domain, and then you're just solving the boundary value problem. Now that's ridiculous, right? You should never try to solve this. Nevertheless, people have tried to do it, and it's actually known as Poincaré boundary value problem. And in Russian school, I think it's called the problem of Sobolev type, because both of those people studied it. And in particular, those people all, going back to Poincaré, but in verifiable work, going back to Fritz John in the 40s, actually worked on that problem for various reasons, sometimes motivated by fluids, sometimes not. When did I start? 22, okay, good. And so how do you solve a boundary value problem for the wave operator? Well, how do you solve any problem for a 1 plus 1 dimensional wave operator? You have a general form for all possible solutions, right? So for usual wave operator, it's f of x plus t plus f of g of x minus t. Well, here, the characteristics are different. So here, I'll have to define what the characteristics are. And so they are constant, they are level lines of these linear functions. Okay, these are two functions. And then you would see that, let me see which letters I use. So then we know that if since my W solves the equation, it has to have this form. W is going to be of x, let's say, is going to be some W plus of L plus of x minus W minus of L minus of x. Like that, I guess. For some two functions, right? That's a general distributional solution on this domain is going to be given in this form. All right, so what are we missing? Well, we're missing the boundary condition, right? So you can see that if you think about, let's say, W plus minus tilde will be W plus minus of x only for x on the boundary. So you just have these two functions, one a function of this variable, one a function of that variable. You can restrict each of them to the boundary only. Then you know that those two functions have to agree. We call it W tilde. That's where the Dirichlet boundary condition is used, right? They have to agree because because this thing has to vanish on the boundary. Okay? So you have to, so you have really just one function on the boundary. Now, that's fine, but there is one more piece of information which we didn't use, and that's actually where dynamics will enter into the picture, and the pattern of this attractor will become more clear. And this is where I should say that this kind of computation is due to, I think, Jian. Certainly it appears in Jian's paper already. There's nothing, you know, it's not quite 100 years old, but it's getting there. This is a simple computation, not surprising that it's been done before. But there is an extra structure here, which was also observed by Jian already, which is given by this chess billiard dynamics. So what we're going to do is I'm going to define involutions of the boundary, gamma plus minus. They depend on lambda, okay, like that. And the rule is this, it's just L plus minus of gamma plus minus of x is the same as L plus minus of x, okay? Here's the picture. Let me draw the domain again. So I have a, or maybe let me draw a trapezoid-shaped domain for later use. And so here's my x. And then what happens is, in order to find gamma minus of x, I just have to trace it. I just have to trace a line of specific slope that's given by this L minus. So it's just L minus equals constant, and I go to intersection with the boundary. And that's what it is. It's easy to show it's a smooth involution, well, under the assumptions that I haven't made yet. And then you can also trace gamma plus of x, right? All right, well, those two involutions, they are involutions, so their dynamics is not very interesting. You iterate them, you just get not much, right? But there are two of them, and they, of course, don't commute. And so you define the chess billiard map. So it's their composition. Okay? So this is called the chess billiard map. Has been studied independently, apparently first in connection with the n queens problem on the chessboard, though I have no idea why it came up there. Yes, so it apparently does come from something chess related. And so here you have x, and then you have gamma minus of x, and then you trace, and here's your b of x. Okay? And now you can repeat this process, right? You can iterate it. And you get some potentially interesting dynamics. And so what you will see in particular, how is this related to this business? Well, you can see that, for example, gamma plus star, w plus tilde, is the same as w plus tilde, right? Because this w plus tilde was just a function of, oh, I'm sorry. Well, you know what I meant there. It's w plus minus of L plus minus of x. It's those two constituents just restricted to the boundary. So w plus tilde was just a function of L plus, and so you would know it's going to be conserved under this evolution. It's an if and only if condition, right? You can, and then gamma minus star w minus tilde is going to be w minus tilde. But they're the same because of the boundary condition. So this means that this boundary data that we get from decomposing our solution has to be invariant under both of these involutions, and thus it's invariant under the chess billiard map. And so that's something that tells you that the dynamics of the chess billiard map will matter at least in the study of eigenfunctions. And that's basically what was done in various of these first line of works. Now, I think it's time for me to erase, and then maybe I'll talk. You know, it takes a little bit of time to erase here. So what I'm going to do now is I'm going to formulate assumptions on the dynamics of this map B. Then I'll write a theorem, and I will discuss some aspects of its proof. Yes, this gives me time to write assumptions. I'm afraid I'll have to squeeze my assumptions. Oh, never do that, I know. Okay. Okay. All right. So yeah, I'll squeeze it here. Here's assumptions that we know. Now you can, for some time, you can forget about eigenfunctions. I just use them as motivation to explain why those maps come up. Okay, where are the assumptions? Well, we assume something I called lambda simplicity, which is a natural assumption that this L plus minus has only two critical points on partial omega, and they're non-degenerate. Okay. So say if omega was strictly convex, that would be the case, but it doesn't have to be like this. The trapezoid has straight lines, but you would just have the critical, you know, if you look at this slant, for example, the critical point would be here and here. I should draw around the corner, and it should be non-degenerate in the second derivative sense. All right? So that will be with us throughout. But there is also more Smale assumption. And what is this? Well, that's an assumption on the dynamics of the billiard map. So under the first assumption, you can see that those involutions in the billiard map are well-defined, they're smooth, and so on the boundary. So the more Smale condition is the following, that this billiard map has some periodic points. Okay? A non-empty set of periodic points. And then that these points are hyperbolic. Namely, the set of periodic points falls apart as a union of two pieces, which we will use later, sigma minus and sigma plus. And sigma plus is the attractor, so partial x b to the n is less than 1 on sigma plus, and partial x b to the n is bigger than 1 on sigma minus. Okay? So this is the attractor. So the assumption is that the derivative is never equal to 1. It's an orientation-preserving diffeomorphism, and you want there to be periodic points, and you want the derivative of the correct, and this is the repeller. You want the derivative of the correct iteration to never be equal to 1. So it's either bigger than 1 or less than 1. Less than 1, then you get the attractive points, and bigger than 1, you get the repelling points. Simple dynamics. Okay, so that's the assumption that I'm going to make, more Smale assumption. Now it's time to, right, I can draw it on the trapezoid. So for example, on the trapezoid, what would happen is you have this attracting cycle. For certain values of lambda, depending on the shape of the trapezoid, it's actually not so easy to have a complete description for which values of lambda. But you certainly can produce some intervals in which this happens. And it's an open condition. You know, if you perturb your lambda a little bit, the dynamics is perturbed a little bit, and this is stable under perturbations. So really, once you get 1, then you get an open interval of lambdas for which it works. And then what would happen here is that this basic attractor that we saw, it doesn't have to be 4. You can make up situation which bounces more. But this is the simplest looking one. It would be sigma plus would be those 2 points, and sigma minus would be those 2 points. So when you go along this geometric shape, you alternate between sigma plus and sigma minus. Always. Okay? So that's the picture, right? So it's just finitely many points. All right, so now I can say, here's a theorem. So if lambda 0 satisfies this more Smale condition, then what can we say about the situation? Wait, so I started this, I should end at this, okay. So I have the following, several things. Well, one is a kind of as a spectral theory result, or it's really a limiting absorption principle. Namely, for any function in omega, nice function omega, and lambda near lambda 0, there exists a limit as epsilon goes to 0 plus minus of p of lambda plus minus I epsilon inverse f. And that's called p of lambda plus minus I0. Okay. I'll take a small break and explain what I mean by the inverse of p here. What happens is, if you look at this operator p, so it's a wave operator, right? But well, it's a wave operator when lambda is real. But of course, in limited absorption principle, what you do is you take lambda complex, and then you'll take the limit when you approach the real axis. Now, if you take lambda complex, you will see that's actually an elliptic operator. It's not self-adjoint, but that doesn't matter. Just get an elliptic second-order operator when lambda is not real. And so for that, you have a Dirichlet inverse. You know, the Dirichlet inverse is well-defined. And that's what I mean by this inverse here. Right? So for HF, you can solve the problem for this operator with Dirichlet boundary conditions. And then you let epsilon go to 0. And in a certain space, which I will not specify here, but certainly weaker than the energy space, so weaker than H1, we show that this Dirichlet solution actually has a limit as epsilon goes to 0. And you get those things that are called, you know, pp of lambda plus minus I0 inverse. Right, so you have a limiting absorption principle. That immediately tells you, for example, the spectrum is absolutely continuous and so on. 2 is, we actually have quite a bit of structure of those because of the way that the proof goes. So these are conormal to the attractor. So if you look at this shape, what you will see is that you're going to be smooth except on the attractor, and on the attractor you're going to be conormal. Of a specific degree, so there's a lot of information, but I'm not going to say more, but it's somehow it's a lot more information than just being smooth outside of it, because you know that you can differentiate along the attractor and you do not lose regularity. Okay, so you have structure of what you actually get. And this is in perfect analogy to what happens in, say, usual Euclidean scattering theory, right? You know, you have limiting absorption principle, and then you have your limiting solutions, and you have their asymptotic expansions as x goes to infinity, right? That's the usual Euclidean scattering theory. Here, instead, we have a description of singularities in a certain asymptotic sense. And 3, well, if we go back to the evolution problem, then the solution of this evolution problem can be decomposed in 3 pieces. So one piece is this fixed solution, which is comes from the attractor, and it oscillates with this frequency, but it's something very explicit in principle, right? And that's what we see in the experiments. We see this attractor. Plus, of course, there's got to be error terms, and there's 2 kinds of error terms. There's O little of 1, but in a weaker space, which corresponds to, so h1/2 minus, you lose half a degree of regularity, which again, if you work with limited absorption principles, is not going to surprise you. Generally lose a half degree of regularity. Well, you lose a half degree of decay there, and here you lose half a degree of regularity compared to H1. So this is small in the space which contains the solution, plus the stuff that comes from the rest of the spectrum, and that's bounded in the energy space. So this is a relatively satisfactory mathematical statement which corresponds to what you see in experiments. Right? Okay, cool. Now, well, let me say just a few words about what happens if this Morse-Smale condition does not hold. So what happens if you're not Morse-Smale? Sure. Oh, well, that requires a computation. So I lifted it from the paper, but well, you can compute. It's just if you So of course, you have to choose the length and the slant correctly, and you have to choose lambda correctly, which changes the slope. But for a certain range of those, which, you know, we have the numbers in the paper, but I don't think I can just immediately tell you what the numbers are. What you see is that when you go around, it's kind of it's almost like an interval exchange map, and so this interval will kind of collapse when you go down. So if you try to iterate, you will this one. Yeah, and they have to alternate because each of those involutions conjugates b to its inverse. So that one is easy to see. That's why they have to alternate. So attractors have to be conjugated to repellers, have to be mapped to repellers by each of those individual ones. Yeah, which is a bit of a confusing feature of the problem because you have one picture, but there's kind of two things going on inside. All right, so what happens if you're not more Smale? Well, so this B is a diffeomorphism of the circle. And there's actually a rather robust theory of even homeomorphisms of the circle, orientation-preserving ones. It's not quite a complete classification of them, but there's not so many things that can happen with them. And in particular, they're characterized by a single number called rotation number. And basically it tells you when you go around many times, how much you are rotated around the circle. So in the case of Morse Smale, so you can see that this depends on lambda because the chess billiard map depends on lambda, on the forcing frequency, right? Because the slopes depends on lambda. That's what it is. Actually, a pretty easy and neat thing to write out, well, the basics of. So in the Morse Smale case, or in any case where you have periodic points, this is a rational number. Again, one of the things I can't show you because I don't have the slides here is if you try to plot a graph of that, say for the trapezoid as lambda increases, you see something that looks a bit like a devil's staircase. So you see rational plateaus, and that's where the Morse Smale condition would hold. And then you see kind of not non-generic for this one, but generic for some other settings, situations where the rotation number is irrational. But you know, it's continuous, and it kind of goes from 0 to 1 as you increase lambda from 0 to 1. So you would know that it's every value of the rotation number is achieved. And so here is a result of Lee in 23, and Colin de Verdier later found a considerably simpler proof of this result, and then they wrote a paper together on that. And so the result is this. So assume R lambda 0 is Diophantine. Not going to write the definition. It's poorly approximable by rationals. Okay? So it's in some sense, a generic number is Diophantine. Then you have two things. One is that the spectral measure of a epsilon interval centered here is going to be very thin. So it's the spectral measure of a smooth observable is going to be extremely thin next to this Diophantine frequency. Namely, the measure of an epsilon interval is going to be decaying faster than e power of epsilon. And two, so that's different, of course, than what happens in the Morse Smale case. And two, from this, you can deduce that you just have energy boundedness uniformly in time, which, given this unavoidable remainder, is the best you can. Right? So the situation is different when you have a Diophantine. Now, I should move on to talking a little bit about the proof. So the proof has a lot of components, but what I should have really done is I should have erased something. Let's see. Yes, you have to, for future speakers, you have to plan strategically when you're going to erase. You should talk while you erase. Otherwise, yes. Well, maybe I'll erase two of those. Maybe I'll erase this also. That should be enough. This one and this one. Or you can write really small and just fit everything and not erase at all. That's probably the most efficient in a certain sense approach. But okay. Well, while I'm erasing, I can tell you what the ingredients are. So how do you prove a limiting absorption principle? There is a lot of possibilities. I don't know where Colin disappeared, but oh, here you are. You could use Moore estimates, and that's what Colin, Divergent, and Saramon did. Or there is an approach due to Melrose, which is a combination of, you need a high frequency component, which is where radial points estimates come up. So this is back from his work in the 90s on Euclidean scattering. So, okay, you need high frequency component for radial, limiting absorption principle, and that's where radial estimates, propagation estimates, and a lot of things that Andras talked about in the morning come up. And after that, you need to exclude embedded eigenvalues. So you need to exclude low frequency problems. All right, I'm supposed to erase while I'm talking. It's hard to erase while talking. And then there is a kind of general function analysis argument due to Melrose, as far as I know, using compactness. That tells you that you have a limiting absorption principle if you have those two ingredients. So you have high frequency plus low frequency. Now, I'll focus on the low frequency because I think it's, to me, it was actually a more striking part of this, though that's not to say that the high frequency part is trivial by any means, but low frequency part was a bit more unusual. So what you need is, well, right, I'm supposed to tell you where the Feynman propagator comes in. So a bit about the proof of that theorem that I think is still there. Let's see. Okay. So the first thing you should do is, well, what we do is we reduce to the boundary. It's very tempting, right? You have a constant coefficient problem just on R2 with a boundary. You can reduce to the boundary. I'm sure there are ways to avoid doing that. But what you do is you look at a fundamental solution. So you have this P of lambda. Let's say P of omega. So omega is complex number. And you just write a fundamental solution. Right? You know how you solve Laplace's equation on R2. And you write a fundamental solution. There's a convolution somewhere. So if omega is non-real, because we're going to be taking limits, right? So you need to understand the problem for non-real values of the spectral parameter and then take the limit. So somehow prove an estimate that's uniform as epsilon goes to 0. So then you can see that up to a constant, this E omega, of course there are plenty of fundamental solutions, but one that somehow comes to mind of x is going to be given by log, well, some constant log of L plus of x omega, L minus of x omega, like that. Now, that's when you look at the log, again, omega is non-real. So if you look at these L plus minus, they are actually maps into the complex plane now, and they're non-degenerate. So, and you can see that the imaginary part here has a sign. So this makes perfect sense, actually, right? So it's a log, right? For the Laplacian, it's log absolute value, 1 over 2 pi log absolute value x, and here you get this. Okay? It's the dual quadratic form to the equation. So now, if you look at the limits of that, so this is just for use since the Feynman propagator is very popular this week, you get log of now this quadratic form. Now you should think of it as like x1 times x2, right? Because now those are two linear, just two linear maps from to R. Right, so you can really change coordinates, think of it as log of x1 times x2, so that could be both positive and negative. So you have to make some choices. Well, here it's going to be plus minus I0. And if you think about it, this is the convolution with this is the Feynman propagator for the 1 plus 1 dimensional wave equation. It doesn't come here from quantum theory at all. There's nothing quantum here. It just comes from the fact that we're studying the spectrum. We're studying the spectral problem for that as you approach the real line from either side. That's the correct fundamental solution to study here, and it does happen to coincide with the Feynman propagator. Okay. Now what you can do is you can reduce to the boundary. And since I'm running short on time again, I'll just talk about that. Since if you know how reduction to boundary works for elliptic problems, you'll follow. Otherwise, I won't have time to explain how it works anyway. But if you have an elliptic boundary value problem, you can write your solution as a single layer potential applied to something on the boundary, which is usually Neumann data, plus this fundamental solution convolved with the right-hand side. So you can reduce it to a single equation on the boundary. You can reduce the situation, kind of all the difficulty of the problem can be reduced to solving a single equation on the boundary, and you need to figure out kind of what's the Dirichlet to Neumann map, or what's the equation that you get from this reduction. Now, if you look at this equation, so that's where some analysis is needed, you can see that you actually get something that looks like identity. For the Laplacian, you get some like identity plus minus, I think, a minus first order term. Here, what you get in the boundary equation that you need to solve, you get identity, plus things featuring pullbacks by those gamma plus minus maps that I erased, the two involutions. And one of them is on positive frequency, and the other one is on negative frequency. It's kind of a funny problem, but it can be analyzed. And the role of epsilon there, of the imaginary part, is it provides complex absorption. And so when you need a limit as epsilon goes to 0, you have to prove an estimate that works in the correct time direction so that complex absorption works with you and not against you, but uniformly as epsilon goes to 0. And this sigma plus minus, which I also erased, the attracting and repelling sets, they are radial points. Except here time is discrete and not continuous, but it actually makes it easier. So by using the technology described by Professor Vashi in the first talk, and enough kind of intuition, you can reduce to the boundary, and you can get a high frequency estimate. All right. There's one thing that also comes up is what about the characteristic points? Because there are these points where where L plus or L minus has its minimum or maximum. Turns out in our specific model, they do not make any difference, which was very nice. Okay, but what this high frequency estimate tells you is that you have to exclude the situation where you have an eigenvalue. Well, it's easy to do for smooth functions. But what a high frequency estimate tells you is you don't get something smooth, right? You get instead something with a prescribed wavefront set. And so you get U, or well, your U is, you can decompose it in the same form as just, you can reduce it to a single function on the boundary. And so this W that's related to U as it was there, so I guess W is just has to have the following wavefront set. It's inside X is in sigma plus, and psi is negative, union with X is in sigma minus, and psi is positive. So on attracting points, you need, I think, negative frequencies, and on the repelling points, you need positive frequencies. It's kind of like an outgoing condition, except it's weird because the frequencies here are split into positive and negative because this is one-dimensional, and you have this kind of split. Okay, now I have just a touch of time. And so you want to exclude a situation like this. You want to exclude having a solution, so this is a low-frequency abstraction. In some sense, you need to exclude a solution to this equation where after boundary reduction, the wavefront set is here. So what we need to exclude is if we go back And remember that our boundary reduced thing was invariant under the chess billiard map. And now we have the wavefront set there. Then you need to show that this W tilde is constant. Because if it's constant, then the solution just cancels. So after all is said and done, it reduces to a very simple microlocal analysis problem in one dimension. And that's maybe where I'll leave you at. I'll tell you a model case. So here's a, it's kind of hard to keep track of all I'm saying. Here's a model case. And that's really, you can assign to a microlocal analyst as an exercise, and it's kind of a neat one. R, you just take R union with infinity. So that's my circle. I just compactify the circle. So 1 over x is a smooth function near x equals infinity. And then let's say your b of x is equal to 2x. So the map 2x is a kind of a quintessential Morse Smale map, because 0 is going to be the repeller, and infinity is going to be the attractor for that map, right? And so now you just know that you have W is a distribution on this. Wavefront set of W is inside x equals 0, psi bigger than 0, and x equals infinity, psi less than 0. And you know that W of 2x is equal to W of x as a distribution. Then you have to show that W equals constant. All right, unfortunately, I ran out of time, so I'm not going to be able to tell you how to do it. But there is a neat microlocal, not even so microlocal argument, using extension to the complex plane and a kind of a Dirichlet integral in the upper half plane, which actually tells you that this is the case in the model case. And that can be adapted to the general absence of embedded spectrum. Because I should say that in those works in the middle, starting from Colin-Deverdier and ending also with Colin-Deverdier, you needed to make an assumption. So for general zero-Thor pseudo-differential operators, you could have an embedded eigenvalue. In fact, Zhong-Kai Tao, I believe, constructed an example where you do. And so you need a spectral assumption to actually make your theorem work. In our situation, we show that there is never any embedded spectrum under these assumptions. All right, I should stop now. Thank you for your attention.